flop behaves. It behaves as a memory state for 0 0 input, and SR flip-flop behaves as for set if S is 1 and reset if R is 1, and it is an indeterminate state when both S and R is 1. The circuit shown here is for SR flip-flop or gated SR latch. So I will show you in case of JK flip-flop what happens is only one extra connection comes, which is the feedback connection, which starts from Q bar and it goes back to J. It starts from Q bar and it goes back to the gate where you are giving J. Same way, from Q it starts and it goes back to the gate where you are giving a K. So this is the circuit of JK flip-flop. Now, because you already know your SR flip-flop, you will remember that it works when it is a gated flip-flop. It works when clock is high. And as you can see, it is a level triggered flip-flop. I am not showing the symbol of pulse triggered. I am simply making it 111, and 111 means it is level triggered flip-flop. Okay, so you know that if you remember your NAND truth table, for reference I will write it also here. If you remember your NAND truth table, I am giving you this only so that you can remember the truth table to understand the working of the JK flip-flop. So what does NAND truth table says? NAND truth table says that if all the inputs are 1, then only output will be 0. So what you can see here, if your J and K is a 0, and if your clock is high, if your J and K is 0 and clock is high, it will be under which condition? It will be under memory condition. You know that if any one of the input of NAND gate is 0, it pushes the output to be 1. So if you remember the working of SR flip-flop, I had told the flip-flop working is mainly governed with this NAND logic, which says that if any one of the input is 0, output is forced to be 1. So you can see if clock is high and J and K are 0, 0. So one of the input of the NAND gate became 0. It will force the output to be 1, 1, and it goes into memory state. Memory state means what? Memory state means if Q was 0. Now see in red color what I am telling, what I am writing. If Q was 0, at n plus 1, it will remain 0. If Q is 0, Qn bar will be, this is our nth time. If Q is 0, Qn bar is 1. At n plus 1 time, it will remain the same. And if Qn was 1, Qn bar was 0 at nth time, because it is behaving as memory, it will remain same 1 and 0. So you can see that for 0, 0, it is behaving as a SR flip-flop only, and it is going into the memory state. We call it as memory state. So this part, no change. Now coming on to this part, next one, when J is 0 and K is 1. So when J is 0 and K is 1, what happens? If your clock is 1, of course, and J is 0, K1. So when J is 0, it will force the output of this NAND gate to be 1. And if K is 1, clock is 1, and your feedback, if J and if clock and K is 1 and 1, the feedback depends, it will depend on the feedback. But let us bother about the first NAND gate only as of now. When J is 0, clock is 1. If any one of the input is 0, it will force your output to be 1. So with J as 0, output of this NAND gate is forced to be 1. And if you remember in your set condition, this sets your flip-flop. Sorry, this will reset your flip-flop. This will reset your flip-flop. What I'm trying to tell is this circuit and your SR circuit remains the same for first three cases. Only the change come in the last case, which is J and K equal to 1 and 1. You remember that for SR flip-flop, your 1 and 1 was an indeterminate state. So this circuit behaves as SR flip-flop until first, second and third case. Only the indeterminate case changes here. So if you remember, your J is uh, replaced from S and K is replaced from R. So I need not tell you the working of this again for these three cases. So when J is 0, K is 1 means it is in reset state. And if you remember, in reset state, it does not bother about the previous input, previous state. It will be simply resetting the flip-flop. It will reset. So whether your in previous state was a 0 or a previous state was a 1, it does not matter. It will reset the flip-flop and the new state will be 0 and 0 only. So this is called as resetting. So resetting remains the same for JK also as it was for SR. You can go through the working part the same way as SR flip-flop came into picture. So your resetting happens whether your input was 0, whether your state was 0 means previous state, whether your previous state Qn was 0 or whether your previous state Qn was 1, it does not matter. In any case, the next state will be 0, 0, and this is called as reset state. So it will be resetted. It is a reset state and your Qn plus 1 will be 0 and 0. And Qn plus 1 bar will be of course 1 and 1. And of course Qn bar will be opposite of whatever Qn was. So this is your reset state, same as your SR flip-flop. Same way your set state is also same as SR flip-flop. In as I already told, in place of SJ has come, in place of RK has come. So this is now your reset state. This third one is your set state. Second one was your reset state. This third row is for your set state. Now set state says what? Whether your input was 0, whether your previous state was 0 or whether your previous state was 1, it does not matter to the flip-flop. Your new state will be set, and set means 1. So 1 and 1 you will get. The way in the previous case you got 0 and 0 irrespective of your previous state. Now for the set you will get 1 and 1 irrespective of your previous state. So this is called as setting of the flip-flop. It is same as your SR. So now these are the main columns. Of course Qn bar will be complement of Qn, and Qn plus 1 bar will be complement of your Qn plus 1. So this is same as your SR. What you have to understand now is only your this second last row. Of course, last row is the case when your clock is 0. It will not bother about the input. So it will become a don't care. So when it is a don't care, anybody will tell me what will happen, which state it will be in if it is in the If clock is 0, what state it is in? If clock is 0, what state it will be in?
Memory state.
Memory.
Correct. So it will be in memory state. So if it was 0, it will remain 0. If it was 1, it will remain 1, and complement will also be same. So it will again be in memory state only. So there are two memory state when J and K is 0, 0 and when clock is 0. Now the only difference here is this state, which I need to explain you in detail. Okay, rest all are same as your SR flip-flop, so I am not going in detail. Now let us come back to your toggle. It is called as toggle case. In case of SR, it was the indeterminate state. Now you need to understand this very carefully. So listen to me in a very attentive way. Okay, now I am assuming your J and K is 1 and 1. Okay, and I am assuming that clock is also 1. Now when J and K both are 1 and clock is also 1, the things will depend upon these feedback only. All these time J and K was your main controlling input. Now J and K is 1 and 1. Now controlling input becomes this feedback. Now you see what will happen. Assuming that your Q and Q bar was in the state of 1 and 1 0. So let me take that state. I am taking this Qn. Let us assume that Qn is 1 and Qn bar is 0. Okay, so I am writing here. I am assuming that previous state Q is 1 and Q bar is 0. In green I am writing this is the starting of my this special state of your flip-flop. So now let us see what will happen. J and K is 1, 1, clock is 1. My previous state says that Q is 1 and Q bar is 0. Now let us see what will happen. When J and clock is 1 and K and clock is also 1, what you will see here, the feedback of Q equal to 1 will go and it will make this output to be equal to 0. Can you see? When clock K and the feedback Q is 1, 1 and 1, the 3 input NAND gate, all the 3 input are 1, 1 and 1. So this will become a 0. And what will happen to this? It is having J and clock as 1, 1 and this Q bar is 0. So this 0 will go in, and as this NAND gate shows, any one of the input is 0, output becomes 1. So what will happen? It will go and make the output of this this NAND gate as 1. So what is happening? When it started with Q equal to 1 and it has made your output to be equal to 1 and 0 here. Are you able to understand what is happening here? Your K had got feedback from Q, which was 1, and this NAND gate which had the input coming as the feedback from Q bar was becoming a 0. So 0, 1 and 1 gave me 1 here, and all the 1 at the bottom of your bottom NAND gate gave me a 0 here. So what state it will go in? If you remember, this is actually S bar R bar here. It is actually S bar R bar. If you remember, S bar R bar says what? It will be making your output to be, or let us make our NAND gate here. So 1 is going here, and what is the feedback here? 0, right? And a 0 is going here, and what is the feedback here is 1, right? So what will happen now? What is the output of this NAND gate? Can anybody tell me? Yes?
1.
Q will be 1 or Q bar will be 1?
Q will be 1, ma'am. Both will be 1 actually.
See, when your any one of the input is 0, output is forced to be 1. And I had told in the beginning of SR flip flop, you should see when your main input comes like this. For example, this down NAND gate, when it comes like this, you need to see this as the main input, and we will see that this is being driven to 1 because your NAND gate says that when any one of the input is 0, it forces the output to be 1. So you will have to see, because the main input is coming as 0 here, we will have to see the working of this NAND gate, and because it will not bother about this other feedback. As soon as it sees 0 here, it will make it a 1. Okay, I will change the color of the pen. It will make the, as soon as it sees a 0 here, without bothering about this feedback, it will make this as 1. It will make this as 1. Now what you will see, this 1 will be going as feedback here, and this 1 and 1 will make this 1 as 0. If you see otherwise, you will see that both is becoming 1. But I told during SR flip flop working also, as soon as the main input comes 0, it will force the output of this NAND gate to become 1 without bothering about the feedback. So this will make your Q bar to be 1 and Q to be 0. Now, when this happens, it started with 1 and it became 0 after this operation. Again, what will happen? This feedback is continued. Actually, what you can see as of now is 1 became 0, 0 became 1. So that means what? It changed its state. It changed its state, and it is called as a toggle state. Now, when Qn is 1, when Qn is 1, it became 0, and Qn bar was 0, it became 1. So this is one case. Now we will have to see our next case in the same fashion. In the same fashion, we have to see our next case. So I will show you the next case now. We will assume that Q was a 0 and Q bar was a 1. Okay, now we will see our next case under J and K equal to 1 1, under this special case. So now let us see, when this is 0 and this is 1, J, K and clock are all 1 1 1 only. So now again what we will see is, now when your Q bar is 1, when your Q bar is 1, so with this Q bar equal to 1, this feedback goes, all the three input becomes 1, 1 and 1. So your output will become 0 this time for this one. And for the down NAND gate, this is getting feedback from Q, which is a 0 now with dark green color, which is a 0 now. So 1, 1 and 0 will make your NAND gate output to be 1 here. So now you can see a 0 on the first NAND gate output and 1 for the second NAND gate output. Now as soon as you see a 0 for a NAND gate input, you need to see that working only, because as soon as a 0 is seen at the NAND gate input, it will force its output to be equal to 1, as I told you in the previous case also. As soon as it sees a 0 here, without bothering about the feedback from the output side, it will not bother about the feedback. It will force the output to be equal to 1. So what will happen? Your 0 will become a 1 here, and here for this second NAND gate, down NAND gate, after this becomes 1, this 1 and 1 will make the output as 0. So what we can see here in this case, when Q was 1, this J and K equal to 1 made it 0. When Q was 0, this J and K equal to 1 made it 1. So means what? It is changing the state. It is changing the state. So let me put it now. When Qn was 0, it made it 1. Qn bar was 1, it made it 0. So it is changing the previous state. So it is called as toggle state. It is called as toggle state, and we generally write it as Qn bar. Whatever is the previous state, complement of that becomes the next output for the J and K equal to 1 and 1. So you saw JK flip-flop, only two things were new here. In the circuit, the feedback is going from Q to Q to K NAND gate and Q bar to J NAND gate. That was the first change you saw. The second thing you saw that all the three cases are same as SR flip-flop and only one case is changed, that is 1 and 1. There is no indeterminate state now. In place of indeterminate state, a toggle state has come, which is this. Is this part clear to all of you? Is this part clear? If any doubt is there, you please ask me. Quickly. No doubt, everything is clear. Yes? The toggle part is clear that when J and K is 1 and 1, it will be changing the state from 1 to 0 and 0 to 1. Now, you people will have to see that when J and K both are 1 and 1, in that case, it is changing the previous state. And this is happening because of this feedback. Because of this feedback, it is forcing one of the NAND gate to give the output as 0, which is forcing the subsequent NAND gate to make the output as 1. So this is happening for the toggle state. Now, one very important thing you will have to understand with JK flip-flop, it has solved one problem. That problem was it is not having any indeterminate state now. So that was something which we never wanted. It is solving that problem. But it is creating one new problem. And what is that new problem? That new problem is called as race around condition. Now, what do you mean by race around condition? You please listen to me very carefully. Now see here, when clock is high and J and K is also high, when clock is high and J and K is also high, then this toggling is happening, right? Now we assumed that Q was 0, then it became 1. So what you will see in the waveform now, I am not showing J and K waveform here. I am simply showing only clock waveform. So when J and K is 1 and clock is 1, it will start its toggling. But the problem is from Q, it will become, I will show with the, as soon as your clock became high, your toggling started. So from 0, Q became 1, right? Now, Q became 1, clock is still high, feedback is still true. So what will happen? It will become 0 again because clock is high. Now when it became 0 again, still the feedback is available, still the clock is high, it will go become 1 again. And this keeps on happening till the clock is high. And when it changes its state so many times, during this high clock level, this is only called as the race around condition. All of you understand this very carefully. This is only called as race around condition. When clock is equal to 0, then it will not bother. It will remain however it is. Again, when clock equal to 1 came, it will start toggling, and at the end of your clock pulse, at the end of your high clock pulse, don't know whichever situation it will remain, it will remain in that situation only for clock equal to 0. Again your clock 1 came, again it will start toggling. So this is the condition when the when this toggling happens, and we do not know how many times it may toggle. Okay, so this is called as race around condition. This is the problem of JK flip-flop for which we are supposed to find the solution. How many times it will toggle, we don't know. Here you can see that it is toggling 4 times, here it is toggling 3 times, here it is toggling 4 times. So whichever state it remain in, for example, in this second one, it remained in 1, it will remain in 1 for rest of the clock equal to 0 time, and as soon again clock equal to 1 came, again the toggling started happening. So this is called as toggling of the JK flip flop, and this is the problem which is called as race around condition. Is this part clear?